Who went to the Navy game? They came back. Came back. It was like the Eagles came back. But all right. All right, this is the new set of slides, chapter 1 and 2. There's like 130 slides in there. All right, so we got some cruising to do here. Yeah.
Can we ask some questions from the homework?
Chapter 2? Yeah. Let me start chapter 2, and then we could probably answer them as we go along. Okay. Yeah. If I can get this projector. There we go. All right. Well, this is just the 8086 stuff. Yeah, well, just again, the reminder of the difference. Yeah, this is, again, the microprocessor stuff has all this external to the CPU, all right, whereas your little microcontroller has everything's on board. Okay, so everything's sitting in there nice and tight. This is what's called a dual inline package. There's different types of packaging. The 8086 and the 8088 are 40-pin DIPs, dual inline packages. Starting off, always in the upper left-hand corner, you'll see a little notch up in here, or a little circle or something that designates what the pinouts are. It goes down to 20 and then up to 40. Okay, and that's actually what it looks like. There's your 8086 sitting in its slot. This is all external memory over here. Again, vintage 1980 technology where you would simply insert in your peripherals, your modems, which you guys don't even know about. You weren't even born then. Your printer cards. If you had any external, like A to D to D to A cards, they would get all popped in those slots. So those are all you can see physically. It's separated out. Where the beautiful thing now is all this stuff resides on a single chip. All right, that's the beauty about it. So again, the AVR CPUs comprised of arithmetic logic unit, status register. Well, actually, arithmetic logic unit, 32 registers starting in R0 through R31. Now, this SREG and this is not sitting inside the CPU itself. This thing sits over at memory location 5F in SRAM, and this starts at, let's see, this starts at 0000 in SRAM, all the way up to here is 1F, all right? Huh? This sits at 5F. I'll show you, because we're going to write to this thing, all right? We've written to something the other day. I think Rachel asked, hey, where did the 9 or the 5 go? That's an SPH. It's the stack pointer high and the stack pointer low. We'll get to why it drops off the 9. But today I'm going to write to this thing, and you'll see the whole thing getting written to. All right. And you got obviously program counter, instruction decoder, and all that stuff. All right. What we're working with are the AVRs. All right. These are 8-bit microcontrollers. Now, can anybody tell me what's the difference between an 8-bit and a 32-bit microcontroller, and why is that? What makes an 8-bit, a 16-bit, or a 32-bit microcontroller, or a 64-bit for that matter? You're close. You're really warm. The data bus. It's the size of the data bus is what it is. Yeah. So here we're working with an 8-bit data bus, and we'll see that in the AVRs. The same thing with the PICs. The PICs have them. The 8051s, which is still an industry. I mean, this thing's been around forever. You know, You can see the PIC series has been completely modified. I think I told you I did a workshop on this, so if anybody's interested in some PIC stuff, I got a whole boards, everything laid out. I mean, I might even we don't want to waste time with that. 32 bits are actually the PIC 32. Duh. All right. The ARM processors, I have some of these. Depending upon how far we get, I'd like to at least open this up around week 12 or 13 to show you. This is really where the industry's going in here. All right. So I want to get you, if we can get right to the edge of where get in front of the wave. We'll talk about some ARM stuff. All right. All right. So the AVR has different groups. All right. Classic AVRs are the AT90s, and we'll show you what all these numbers mean in a minute. The Atmega 8, the Atmega 32. This is the one that your author uses in the book. All right. Last year it was a 2560. All right. So we were using the Atmega 2560. Again, a very popular one. I had a call from Eric Cordes over in biology. He's the guy that does all this deep sea stuff. They have this ROV, and they were soldering to it, and what was the processor that was in there? It was a 2560. So they want me to come over and fix it. Biologists don't know how to freaking solder, man. They burned it out. So, all right, whatever. The Atmega 128s, the 25. It's all different memory, different peripherals, all that kind of stuff. You got the tinies, you got all this stuff. So the AT90s, I mean, your code ROM's really tight. I mean, you got 2K. That's why these things are so tiny. It's got 15 I/O pins on it. The other one has 3 I/O pins on it. The EEPROM is 128. The RAM that you're working with is 128. I forget what the SO stands for, something integrated circuit, but it's a dual inline package. It's basically how the chip is laid out and how the legs are on it when you surface mount this stuff. You know what I mean? When you physically get the thing on the board. That's what all these packaging and pins are different. This is a quad flat package. That's what we have on the butterfly board. You'll see this in a minute. All right. Some other ones are the Atmega 8, the 16, 32, 64, 1280s. And again, these are all quad flat packages. Or you can get them in dual inline packages. These give you the pin numbers on it, how many pins are associated with each one. All right, those are all little legs coming off the guy. All right. Let's see. Then you can get the tiny ones. There's a reason why they're called tiny. You don't have much code space to play around with. All right. You don't have much RAM to play around with either. All right. So these tinies are tiny, and again, they're very special purpose ones. If you're going to stick them in your washing machine, in your cell phone, these are used inside here for a Bluetooth or something. They're very specific chips that are programmed, and I mean, you're going to sell 1 million of these. So that's why you go for this stuff. I mean, when you're talking pennies on for the price of an individual chip, and then you're going to do production run of millions of these things, that can add up. All right. And here's just some other ones: the controller area networks, the universal serial buses, the pulse width modulated ones. Here's the one we're working with, which is our 169. The nice special features about the 169, I'll get to them in a minute. It has nice displays. All right, so this is your dual inline package stuff. This is what they look like. Dual, both sides. They plug in sockets. And I forget which one this was for, but this is a 40-pin dip. These are your quad flat packages. This is what we have, actually you have to have. You'll see if you really look close in the upper left-hand corner. There's usually a little notch. That's where you know pin number 1 is. All right, and then it works down and then back around and up the other way. The quad flat packages works this way. You got, again, a little dot there. If you go down the left-hand side, it goes from 0 to 11, across, up, and over that way. So you specifically know what pin is for what. All right, and that's typically, there's a Zilog one right there. That's a quad flat package. All right, so what do these things mean? The AT stands for Atmel, obviously. The Mega is a group. The 169P has 16K of flash, okay? Again, the Atmega 128 gives me 128K of flash. The Tiny 44 It's tiny because it's part of the tiny grouping, and it has 4K of flash. When I say flash, I mean your book and whatever, it's program memory. Not data memory, it's program memory is flash. Okay, so those two are synonymous. Not SRAM. SRAM is different, all right? So you've got the Mega 32, which is what we're using, the author uses, has 32K of flash. It's more programming space.
So, what does the 9 stand for in 169B?
I'd have to look that up. I'm not sure what there's something with the 9 and the P. I have to look it up, but yeah. There's a 160, there's a 16. I know when we get to Atmel Studio, let's take a look at it. There's a reason where the 9 and the P are from. And again, Classic Group 90S is a classic group, the first 4. And again, what all these numbers mean, there's thousands of these things. I don't have them all up here. All 3 neurons can only hold on to so much memory. And it's volatile memory here, all right? When you have a little drinky poo or a little smoky smoke, it's volatile, man. All right? All right, yeah, so there you go. So you got the Atmega, there's a 69A, a 69P, PA. And again, this is just the ones that we're looking for here. So you'll notice that the numbers here are all the same. All right, you know what I mean? As far as the EEPROM, the data, and that. It's probably with the packaging of it. You can maybe have more I/O ports. I could look it up. Yeah. All right. So we're going to take a look at a little overview of this guy, the architecture. I'm going to spend a lot of time on memory today and Wednesday. All right. So that's what your butterfly board looks like. You will be getting this in lab within a week or two. It's a beautiful little board. It has an LCD display here, so we can write things to a liquid crystal display. All right? It has a joystick over here with a button. This joystick can go up, down, left, right, and a button to push it that way. So it's a 5-function joystick built on board. We have the big thing here is the reason we bought these boards is that you can keep them, but we're going to be using this JTAG, which is Joint Task Action Group integrated, in-circuit emulator. And what's nice is we can as this board is running, we can watch and see what's happening with registry, memory, and things like that. But we will be doing our programming from your laptops or your desktops will be programmed in through that JTAG right into here. All right? That's going to get, think of it as your USB connection to your Arduino. That's what it is. Okay? We're going to have 2 I/O ports that we have access to. There's other I/O ports that are built onto this chip. They only bring you out port B and port D, and we will play a lot with these extensively. All right? There's a UART, which is a asynchronous receiver and transmitter for RS-232 communication. All right? So once you have this board, if you don't want to spend the $60 on the, for using it down the road for senior design or something, if you don't want to use the JTAG, you can use the RS-232 communications. All right. There's a 10-bit analog to digital converter on here. All right. Beautiful thing. It has a built-in temperature sensor in here. We can actually go and use the analog. You don't even see the temperature sensor here, but it's built in. So we don't even have to buy a sensor. We can use the one already in there and sample it. Show you how to do analog to digital conversion. They don't, on the boards that we have, we don't have the photoresistor on it. If you want to put one on there, they're a dime a dozen. Less than that even. All right. And here's my port D. The only thing is, well, you'll see, there's going to be some issues with these ports because they tied so many of the I/O stuff together. If I'm using this port, maybe I can't use some of the joystick. I have to deactivate the joystick. It's just how they crammed a lot of I/O stuff onto this board. So yeah. All right, this is what the back of it looks like. There's a battery back there. Don't use the battery. I think I showed you. I had a battery pack with some double A's in it. Because if you use that little button battery in the back, it conks out in about a half hour. It just doesn't, You got your data flash, the 169p. It's a quad flat package. There you can see it. That's it. Quad because it's all four sides. Flat package because it's flat. Okay. We have a speaker on the back too, so we can generate some tones. All right. So the nice thing about this board, it's very cheap, but it has a lot of functionality onto it. We can play with a lot of different I/O stuff, and that's I think what's just cool. The block diagrams looks like this. Here you've got your 169 sitting here. You've got your JTAG, port B, D, UART, USI, ISP, your speaker, your joystick, LCD, the data, and here, this is the stuff for the LDR is the light dependent resistor, which is that photocell that goes right up there, and then there's a temperature sensor that's internal. You don't see it, but it's in there, and then we've got VIN for my analog to digital converter over here. Okay, that's what this stuff is, and this is basically if you want to. Again, if you want to use a serial RS-232 communication, most of your laptops don't even have an RS-232 connector on it, but you can get an RS-232 to USB, converter. Okay, so you can use it that way. I'm doing this right now. I'm playing around with this right now, so it gives you an option. I haven't done it yet, but it's sitting on my little workbench. And here's on my little workbench. This just shows you. Here's port D. Here's port B. There's my JTAG. I have to solder the connector in there. But this was just jumping it over to some LEDs and lighting up LEDs. Okay. All right. The architecture. What does this guy look like inside? It's an 8-bit because my data bus is 8-bit. It's 8-bit data bus. All right. What I have over here is notice over here, let's follow this around. Here's flash program memory. What comes out of flash? Where does it go? To the instruction register to get decoded. And out of here comes all the control lines. So when you guys were doing finite state machines back in digital days, that's the output of the finite state machines, the decoded signals from the instruction. That's what activates. I'm going to a port. I'm talking to an SPI. I got an I2C bus, something, So that's what happens here. And notice what's right here before the program flash. The program counter has to point to the line of code in here, the instruction, it's going to get it. So all this over here is doing fetching, decoding, and executing. So that's what's happening over here. We have a status register that's going to tell me what's going on with additions, subtractions, all kinds of stuff, carry bits, 0 bits, all that stuff. There's a 32 by 8 general purpose registers. Now, on this architecture, they have it separated out. Notice down here we have SRAM. All right? So we've got the SRAM over here that we can write to, and we have the 32 general purpose registers. This and this are really inside of each other, okay? I'll show you this in a minute because we're going to write to SRAM, and you're going to see you're going to actually be writing to these registers. You've got your other EEPROM. I think there's 512K of EEPROM, and then my I/O lines. I can hang on these I/O modules. I have an analog comparator, watchdog timer, the serial peripheral interface unit, and an interrupt unit also that is there. So what we have is these registers are in SRAM. It's volatile, but it's really fast, and that's what I want to do. I'm going to get stuff in and out of there in a hurry. So these guys are really, this SRAM and this are really quick. Over here, I've got my 8K by 16 bits of flash, okay? It's a fast read, single cycle, so I can read an instruction in a hurry. However, it's very slow to write to. I usually don't worry about this slow write because once I got my code and I'm done, I write it and I'm done. Unless I have to keep going back and modifying it. So these registers are won by, they're not even a K. They're just a register. It's a 16-bit register, 16-bit. Okay? You got 1K by 8 bits down here. Okay? For your SRAM. And again, it's fast access, 2-cycle, volatile, but it's not connected to the ALU. These general purpose registers are connected to the ALU. When you're going to be adding, subtracting, doing that kind of stuff, you're going to be using R0 through R32 is where you're going to stick your numbers in, and then you're going to add R16, R21, all right, or whatever. Multiply R16, R2, stuff like that. And then I have my EEPROM down here. It's 512 by 8K. Again, slow access. This is around 10 cycles. Non-volatile. If you need to store parameters for, let's say that you're going to use this 169P inside of a engine control module, and I need for that Nissan Sentra engine control module parameters, that's where you'll stick them. They'll be burned in, they'll be written into here so that you don't have to keep writing for my engine control. I said a Nissan because my driving down 309 on Saturday to get to my tee time at 8:12 for my club championship round, my engine control module fried. All of a sudden, the brake light starts going on, the battery light starts going on, the speedometer and the RPM are doing this, the safety bag unit starts doing this. Well, it was the engine control module that was shot. $653 later, all right? That's okay. All right, just a quick thing on where these are. This Watchdog timer, I just wanted to bring up a quick clip on it. This is obviously the Mars rover. There's a Watchdog timers are essential when you're doing remote stuff, all right? When the system freezes up, you want to be able to reset it. And this Watchdog timer stuff is what it does. So you got a communication link between here and Mars of about 20 minutes. So this has got to do a lot of stuff on its own, all right? This guy just caught up to, the comet is Churyumov-Gerasimovs, whatever. This is a picture, I think this was in, this was taken back in, this is actually the spacecraft itself. It's called the Rosetta, and they have a little robot that's going to come down and land on the comet. I mean, pretty freaking cool stuff. This is the comet. I think this was back in. No, wait a minute. Whoa. Yeah, if you notice here, January, you launch it, you get it on its way, it goes to sleep because you want to conserve power. All right. The Watchdog timer wakes it up. Says, okay, we've got to get you going because now we need to start communicating. Last August, we just rendezvoused with the comet. The lander's going to come down and actually sit on it well, going to be pretty soon. And if I think I have a link here, let me just escape out of this for a minute. I gave you a couple links on that slide. If you grab the one link on the lower left, and then just open up the Explorer, and if you go up and you paste that guy in, you hit it. This is a BBC. I got this off the BBC. That's actually, it looks like a little rubber ducky. This is the head, this is the neck, this is the body. The size of this comet is about half the size of London. All right, that's the size of the thing. The circles that you're seeing here, these are landing spots that they're thinking about for that little robot. And the comet itself, it's a big one. It's 10 billion tons. You don't want it to hit us, okay? Life would be out of here. These are some other. Here's a better. Because actually, that's why they call it the rubber ducky. You can see its head here, neck here, body here, but yeah, it's a little cutie. But that's where they're going through right now, as we speak today. These images came up last week. They're literally hovering. They've caught up to it. They're sitting right there on top of it. So again, all this stuff has to operate in an autonomous mode. So that processor is just like the processor in your car, your exercise bike, whatever. It's running this stuff. So it's got to be doing real-time vision, data acquisition, sensing, and all that. So, all right, I thought I'd just get that up there just to bore the hell out of you. It's all right. All right, so I'll speed up on the timers. You can read it as well as I can. All right. Flash program memory, okay? Again, 8K by 16 bits. It is addressable. You got 8K of addressing, all right? If you notice here, it goes from 0000. How many bits are in here? What does this mean? Hex. So that is how many bits? 4. So this is 16-bit. However, we were addressing here only up to 1FFF, all right? That's what we're addressing to. So how many bits do I need to address to 1FFF? 13 address lines, all right? We're going to show you this in a minute. You got to be real careful about knowing what processor and how many addressing lines that you got. Because if you run something on the 169, and you start addressing SRAM outside of SRAM, things will get interesting. I'll run some of this stuff in a minute. You'll see what's happening. Now, in this flash, sometimes we're going to have to organize things a little differently. There's usually some bootloader code that sits all the way up at the top. Depends. Sometimes we have to jump around it, and that's what we use the org command for. Let's see. So, yeah. All right. So don't worry about the bootloader stuff. That's advanced processors with Dr. Death Szilagyi. So, got a lot of read, write, and erase cycles. All right. The SRAM, again, it's 1K by 8 bits. The SRAM, now again, it depends upon the chip that you have. In all of the AVR series, 0 through 1F is the general purpose registers, okay? Now we get to something a little different, the I/O and the special function registers. This can vary based upon the chip because it depends on how much I/O and how many special function registers you have. Then you typically have your RAM, and so this can start in different places. Now we're going to write to this one right here because 5F is a special function register. This is actually the status register. If you write to 5E, you're writing to the stack pointer low or high. You write to 5D, you're writing to stack pointer low. If you write to other places in here, you're writing to timers, you're writing to analog to digital converters, you're writing to very special purpose stuff. You really don't want to write in here unless you really, really know what you're doing. You had your hand up.
Yeah, where's the EEPROM?
That's external. It's not on here. It's external. It's a different, here, let me go. Oh, there we go. It's external. It's off. And if you go back, oh, I think I went too far. Where was it? Oh. No, it doesn't show it. Shoot. It's inside of here, but it's just, you can write to it. Okay, sorry. Whee, having fun here. All right. So yeah, so it depends on how much RAM that you have. We can go up to, what do we have, 8K? Well, we'll write to it. We'll show you what it. But again, this I/O, you've got R0 through R31, 8 bits are in here. This TWBR, TWSR, There's ADC, analog to digital converters, all that. When you're doing this stuff, you're going to be working with these special function registers. All right. For now, we won't be playing with them. We'll be looking at them, but we won't be playing with them. All right. Let's see what we want to. All right. So the GPRs are 32 bytes of data. Okay, that's it. Just 32 bytes, and it goes from 0 to 1F. That's where they're at there. All right. Then you have the I/O. This stuff is dedicated to specific functions, status register, timers, serial communication, I/O ports, analog to digital converters, all that other stuff. Each I/O memory location is fixed by the CPU designer at the time of design because it's used to control the microcontroller, all the peripherals that you're going to talk to. Okay. The I/O memories, again, it's comprised of 8-bit registers down here. The number and locations in data memory set aside for I/O depends upon the pin numbers of the chip. So what I'm saying here, gang, is this in here can vary up and down depending upon the functionality of the chip that you have. Okay? The more functionality, the longer that space is going to be. Okay? All right. Let's see. Special function registers, you'll have at least 64 bytes that are set aside. At least 64 are set up. It's different for the different series that you have. And AVRs with more than 32 I/O pins, like the 64, 128, 256. Also, if you have extended memory, contains registers for controlling the ports and the extra peripherals that you got. I don't know why this keeps repeating itself, but if you look on the left-hand side, this is for the Mega 64 up to the 128s. This is the memory map for it. And over here, you've got the 64s, the 2560s. You've got a lot more stuff going on here. All right, so on homeworks, quizzes, and exams, and the projects are all going to be 1/6. I have to tell you what chip you're going to use. We're always going to use the 169P, just about. But I will talk a little bit about the 2560 because that's what we used last semester. All right. I will mention it, but we're really not going to work with that much. Some of the material will be on my slides. We'll be working with the ATmega 32 because that's what the book uses. All right. So your homework problems, do the homework problems out of the book using the ATmega 32. That's the default, unless I tell you otherwise. Okay. All right. 169P. It's you go from 00 up to 4FF by 8 bits. So my memory and my data addresses are the 32 8-bit registers. They start at 00 up to 1F. My I/O and special function registers start at 20, which is the next location right after it, all the way up to FF. And then my SRAM, I can start at 1 and I go up to 4FF. Okay, that's how the 169P is set. Gang, you got to know this stuff. This is what you got to know, and when you're going to be reading and writing and doing all kinds of stuff. That is an important thing to have. This is the 2560. Notice you got the 32 registers, you got the 64 I/O registers, and up here you've got 416 external I/O registers. It's not like you've got 32. It's not like the that you've got here with the I/O and the special function registers going from 20 to FF. This guy is huge. It's just that's why it's the Mega 2560. You've got 8K of internal. So over here, when you're reading and writing on the 2560, you're reading and writing to 200 down to 21FF. Over here, and again, this is the difference. You're writing from 100 to 4FF. All right, that's what you're doing there. All right, that's that. So that's my SRAM again. All right. So my program memory, which is flash, 8K by 16. Upon startup, boom. Here's my code is sitting all in here. All right. SRAM sits down here, and there's the other EEPROM. We can write, once we get this guy going, we can then start dumping data in and out of SRAM. We can read it and write to it. We can also do the same thing with EEPROM over here. Let's see. Again, we went through this. This is like a fast read, slow write. This is a fast access for the SRAM. It's just different technology. And again, you got your EEPROM over there. All right, the instruction set. There's 142 of them. I'm not going to go through every single one of them. I'll go through the main ones. All right. This is stuff that you can learn on your own. All right. 16 and 32-bit instructions. You got arithmetic, control flow, data transfer, bit manipulation, logical, and other ones. It's all summarized in Appendix A. Okay? All that stuff is sitting down in Appendix A for you. All right. It's again important to understand what device you're going to use. The homework, the book uses the Mega 32. All else, you'll be directed what to do. All right. Some of the instructions. We'll bang out these, and then we're going to run a couple of examples on the Studio 6. How are we doing on the clock? 36. All right. All right. All right. Load immediate into a register, and it's R0 through R31, and K is just give me a hex number, give me a decimal number, give me a binary number. Examples are load 5-3. Now, when you do a 5-3 without anything in front of it or anything behind it, what is the 5-3 default? That's a decimal number. It will convert it to a hex number, is what will get loaded into that register. All right? 132, same thing. You cannot load anything higher than an 8-bit register that can hold. Okay, you can't load the number 1,000,000 into an 8-bit register. That's when you got to get into multi-precision arithmetic. All right, loading in, this is a hex 27. Hex 27 goes in. All right, here's the instruction. Man, I'm doing a lot of talking. All right. I'm not going to bore you with all these. We will exercise all these, though. Load, when you see an S on it, that comes from SRAM. I'm going to load something from SRAM into a register. So load direct from data memory, and you will notice anytime you see these two brackets, it means that what's in here is an address. That's an address. So without the brackets, it's a number gets loaded in. With the brackets, it's an address. There's also what's called load indirect. Go to the address pointed to by that and load that in. All right, we'll get to indirect addressing. The X, we're going to have 3. Now again, I can go out and I can address in SRAM up to what? How many memory locations? No, come on, let's go back to SRAM. All right, it can go up to, how many bits is this address? All right, let's put it this way. How many bits is that? 8. 12. So now, if I'm going to use an 8-bit register as an address, how the hell am I going to get over 8 bits of addressing? I don't know. You see what I'm saying? If I'm going to use an 8-bit, if I'm going to use an address in SRAM, which is 8 bits long, how do I generate an address that's going to be bigger than it? All these special functions, all the registers are all 8-bit. We're going to use what's called the X, the Y, and the Z register. The X register takes R. All right, the Z register, I'll work from that one. It takes R31 and R30. Those two together will form a 16-bit address. All right, so that takes care of R31 and R30. R29 and R28, that's going to form what's called a Y register, which is a 16-bit address. And then the other two registers right before that are going to form the X register. Okay, so the X, Y, and Z are used to generate 16-bit addresses. Okay? Now you'll see the little plus sign here, and you'll see a minus sign. When you're loading in those addresses one after another, like in a loop, if I got to scan through a table, This doesn't, if I load this, and let's say the X register has sitting in it 00000. When this command is completed, it's going to have 0001 in it. When I do it again, it's going to have 0002. This is what we call load, indirect, and post increment. So you're incrementing, I'm sorry. If you put a minus sign in there, you're going to decrement through it. And you could do the same thing with the Y, same thing with the Z's. I could also do increment and decrement with the Y. And here I can also add on a displacement also. So if I want to go to what's in the Y register and then say, okay, jump 8 locations up or 8 down, I can just give it a number right here. Okay? Same thing with the Z. All right. These are just some examples, adding, whatever. All right.
Professor,
Yeah.
just a moment.
Let's grab this code and bring it into Atmo, and we're going to run this. Yeah. Go ahead.
How do you call the low part and the highest part of X, Y, and Z?
All right. For the Z register, all right, I have R31 is called ZH, which is the high part. R30 is ZL. That's the low part.
It's the same thing if I use R30 and R31.
Anytime I talk to the Z register, I'm talking to R31 and R30. R29, R28. Oh, I'm sorry, Y high. Y low. R27. R26. That's how it works.
But I mean, what if I use the instruction LDI with ZL and ZH, like to load and read it?
That's not a command.
It's not a command?
No. You'd have to load in. If I want to get ZH, I load in R31. They're the same. These are equal.
So if you're doing 16-bit arithmetic, do you need to use those registers?
You need to use multiple registers. 16, yeah. That's called extending. We'll get to it. I'll show you some examples. All right, grab this code. Let's get a new project here. Run the assembly. All right, we're going to run this for several different devices. Let's start off with the 169. Pick your tool. Simulator. All right. Let's take a look at this. It's all right, man. I know it's Monday morning, man. You know, I got a mile and a half in the pool, man. I'm ready to go. All right, so I mean, I hate to terrorize you at 10 o'clock in the morning, but you're all right. Michael, without the A, without the A. Gotcha. All right. EQU. What this does, it equates this sum to this number, this hex number. We're going to use this to so whenever I do something with sum, I'm going to be doing something with memory location 300. They are equal. They are one and the same. If I do something to memory location 300, I'm doing the same thing to sum. All right, what I'm going to show you here is just I start at the beginning of program memory, load in 25, load in 34. So this is just different ways. This is 25 hex. This is also 25 hex if you want to use a dollar sign in front. These two are equal. If I want to load in a binary number, 0B followed by the 8-bit binary number. In this case, it happens to be 3, 1. We add them. Then I'm going to load in a decimal 11, which is B, in hex, add them, store the sum here. All right, so let's do it. Run it down. Run it all the way to the end. Now, go over to Program Flash. Go down to IRAM. Go to click instead of 100. Now notice, real quick. Notice when I hit IRAM on the 169P, where does it default to? 100, because that's the first memory location. All right? And it goes from 100 up to what? 4FF. Right? So that's what it goes up to. So now if you go, just take that 1 and make it a 3 and hit enter, there you'll see the result there. There's my result right there. Okay? There's my result right there. Okay? Now, the games will begin. Change that to add another 0 on here. Add another 0. Add another 0. All right? Is everybody okay with what I just did here? All right? Any questions? Do you have any chapter 2 questions yet, or are we working them out? We didn't hit a chapter 2 question yet? Huh? Good. All right. Because if I don't, I want to make sure you get your money's worth. All right? All right. So now you can see that we've written we never said STS, 300 R16. We didn't have to because sum is 300. Now let's make it 3,000. All right? Do a build. All right, now this will be interesting. Let's run it. Go to memory location 3000. What do you see? What happened? For what? What's SRAM go in 169P up to? 4FF. It didn't tell me, didn't give me an error. And you see an error? Now the question is, where did it go? Now hold it. How many bits, how many address lines do I need to address SRAM? 13. I've used a 3 here. Here's how many bits is that? 12. The 3, let's go see where the 9, we're on the hunt for the number 95. All right? All right, let's go to change this 3 down here to a 0. There's the 95. It's sitting, and if I notice, look at R0. Who wants to tell me what happened here? How many address lines did it use? See, I had 3, 0, 0, 0. So it looked at this one. That's a good address. That's a good address. That's a good address. What happened here? It's not addressable on the 169P. Let's do a quick change, gang. Change this to, go up and click on, all right, you got to stop debugging. I know we're right on the envelope here. Hit this, go to change the device, put in there 2560. Hit OK. We're now just switching the device. Go back, rebuild it, run it. Now look at memory location 30. Where'd it go? All right, I got to check. There's something happened here. Oh, it didn't change the device. Yeah. All right. I'll see you on Wednesday. Plenty of stuff to play with.